Hello, everyone. Welcome to today's webinar. I'm Sam Anderson, Technical Marketing Manager here at Epic, and today we will be showcasing some data visualization techniques for digital twins. Digital twins have increasingly become a popular approach to contextualizing data. If you are still a little unclear what exactly is a digital twin, that's okay. There's many different definitions out there. The beneficial aspect to digital twins is that it allows for analysis of patterns or gaining quicker insights, which provides opportunities to optimize time and money. For instance, they could be used to collect traffic data and improve traffic flows in cities. They could also be used in manufacturing to monitor equipment or assist in training. Digital twins have been used in aircrafts to inform when maintenance is needed, and they could also be used in office spaces to monitor airflow and temperature, which is what you will see today. Today, we will get to take a look at the WSP plugin, which includes a physical entity that uses sensors to gather real-time data, a 3D replica of that physical entity, and a connection between the two. With the tools in Unreal, the team was able to effectively visualize the data. The team has so kindly shared the project with everyone, so the project you will see in this presentation is available on the marketplace for you to follow along in the future. Today we are honored to have Ludwig Loven on as a guest. I'll let him tell you a little bit about himself and the plugin, and then he will get into some of the specifics of data visualization.
Hi everyone, and welcome to the Visualizing Data in Digital Twins with Unreal Engine webinar. My name is Ludwig Loven, and I'll be your host this time of day, wherever you're watching this from. So, I started about 10 or 12 years back consulting in the AEC industry. So, over the years, I've done all kinds of stuff from ArchViz to structural design to BIM coordination to application development. And currently I'm the head of software development at the WSP Digital and Information Management Department in Sweden. So we're a team of developers, both web and Unreal and other stuff, that are creating products for internal and external clients in a few different areas. So one of the areas we're looking into is digital twins, and that in the sense of connecting a 3D model of an asset to real-world sensor data. So the thing we're looking at here, we created over the last year or so. It's the Azure Digital Twin Link plugin and sample project, which is available on the Unreal Marketplace, free and available to download. And this is created sort of as a proof of concept to show off how you can use Unreal to visualize the data in your digital twin. So what we're looking at now is the packaged version of the sample project. And today I thought we'd have a look at specifically the particle systems, a few ideas for how you can use Niagara particles to simulate and visualize sensor data. So, but first, let's do a quick run through of this thing. So we started off by doing a point cloud scan of the WSP office. So the full scan is much larger than this area, but we chose a small area for the demo. And then we created a Revit model based on the scan, placed some fake sensors at fake locations in the Revit model, imported all of it into Unreal Engine. And that's sort of the basis for the whole model here. And then we have the plugin on top of that, and the plugin talks to the Azure backend, and then we have a device simulator that sends simulated telemetry to the IoT hub in Azure and all that. So we have a few different view modes down here. So first, if you select rooms, first we get an overall view of the digital twin hierarchy, number of rooms, number of sensors. You click on one, you get the sensors in that room. You click the sensor, you get the live data. And then we have the 4 different sensor view modes. So first one for occupancy sensors, which track people at desks. So right now we have 4 busy little bees sitting working at their desks. And as the sensors turn on and off, they walk out and in from the office. So this is actually using the AI pawn and pathfinding and that kind of stuff for them to to walk back and forth from their desks. And then we have the lighting sensors. So this is just using a simple point light, which is on and off. Oh, and by the way, all of these different view modes, they have their own time series insights graph. So this is a little web app that's running inside the Unreal Engine that's being displayed straight from the Azure backend. And then the 2 view modes we'll be looking more closely at today. So first the HVAC sensors. So these each have airflow and temperature values coming in. And then these values are being visualized using Niagara particles, which are being spewed out from these vents here. And finally, we have the temperature view mode, which is using static cube-like Niagara particles to visualize sort of a 3D temperature gradient field. And one cool thing about this is it's actually using the level geometry. It's reacting dynamically. So if I were to put up an extra wall, the temperature would propagate correctly. It's using like a 3D pathfinding algorithm almost to find and interpolate the temperature. And this would probably work in 3D as well. If I added an extra floor, it would find its way up the stairs and all that, but we haven't tested that. So that's a quick overview of the sample project, and next I thought we'd have a look at how to set this thing up on your machine. Alright, so the first 2 things we need to grab are the ADT Link plugin and sample project. So just go to Marketplace, search for ADT, and just grab both of these. Once you've installed them, you can just scroll down in this description here, and there is a link to the full documentation. So once you go there, you're taken to the GitHub repo page that has the full documentation and setup, showing the architecture, describing the different components of the Azure backend, and sort of all the steps you need to go through to set this up. So when you set up the Azure backend, it will look something like this. I'm not going to do the full setup now because that takes quite a bit of time, even though most of it is automated. So you will have a resource group with a hilarious name of your own choosing, and then that resource group will be filled with the different services. And then through the, you would use the Cloud Shell here to set everything up. And then you can use that to download the configuration files. They should be here somewhere. This one, and then the mock devices, that's also in another folder. But all that's in the documentation, how you would get those. And then you would also need to clone and download the mock devices app. And to run that, you need Node.js, as it says here. So after you've done all of the setup steps, your local machine will have these files on it. So they will have the mock devices app itself, and will have the configuration file for the mock devices, which describes all of the different sensors and what values they will be sent and how they will send it. And then you would have the config for the Unreal plugin. So this will be loaded into Unreal Engine in the next step. So to start the device simulator, we just go to the command prompt to the folder you have downloaded in. And if you have Node.js installed, you just type npm run app. So this will launch the mock devices application. And then once you are in the mock devices app, you just simply hit add save here. And then you load save from file system, you browse for file, and then you load the mock devices config. And then once the config's loaded, you can see all of the sensors are in here. You just hit power all. So now if we open the log here, we can see that the start is a bit staggered as part of the config, but within a minute or so, all of the sensors should be beginning to send telemetry data to the IoT hub in the Azure backend, which will then relay the information through an Azure function to the Azure Digital Twin service. And from there on, our Unreal Engine plugin will be able to connect to that and get the data. So with that done, we have everything outside of Unreal set up. So now we're all good to just launch our sample project, which we downloaded. And when we load Unreal, it should look something like this. And the first thing we need to do is make sure we have Show Plugin Content enabled under View Options. So that way we can see our ADT link content. So we just go there and we go to Utility and we launch the Editor Utility widget for ADT link setup like that. So this takes care of the whole setup on the Unreal side. So here we can load the configuration file that we downloaded like this. If there's not a communicator in the level, which is a blueprint that talks to Azure, then we might need to spawn one. Otherwise, we can just validate the connection, make sure it's all good. Next step would be to create model. So this is model as in digital twin model. So using Microsoft's Azure Digital Twin language, we have defined some sensor models. So these are defined in Blueprint using an inheritance hierarchy. So this Blueprint air temperature sensor inherits from temperature sensor, and that one inherits from sensor probably. And their values are being defined in the construction script here. And once you select one and you hit convert to JSON, then they're being serialized to JSON with all the variables in the digital twin description language and can be uploaded to ADT. So once you have all your sensor types uploaded to ADT, you can load them into the level. So this also, of course, lets you create new types of sensors with new types of values, as long as you sort of master the digital twin description language. But we're not going to go into that today. And then we can edit our sensor types if we want to, which we don't right now. So now we can go in and create our twins. So we can go find twins in DS, which stands for Datasmith. So these are all the sensor locations that are being imported from the Revit model. So we just hit select all and we create selected twins. So this should be spawning all of the different blueprints that we need for the sensors and the rooms and all that in our level. So hopefully by this point we are done with the setup. So now if I just go and hit play on this one, this should be pretty much the same thing as the package sample project we looked at earlier. So if I go to HVAC, yeah, you can see the HVAC sensors are doing their thing, and the same with the temperature. Cool. So let's have a look at these particle blueprints. So if we start with the temperature one, so how that is being done is there is a temperature blueprint already placed in the level, which contains a particle system. So you can find this under the sample content, particle system, and temperature. So this blueprint has an event bound to it. So that's done in the setup. So just when the level starts, it just finds all the temperature sensors and it binds an event so that when the temperature is updated on the sensor, it triggers this blueprint to recreate the whole particle field. And it does this by setting array values on this Niagara system like this. So there's an array of temperatures. and then it reinitializes the system. So this is a Niagara actor blueprint. It has a Niagara component and all of that stuff. And this is really everything that's in the blueprint. This is just some visibility toggling for switching between the view modes. But as far as particle system goes, this is it. So all of the heavy lifting here is done in the particle system here. So inside the particle system, you will have something like this. And one thing that I've changed from the version that you have is I've tweaked these parameters for temp values, because they should really be in the range of 0 to 1 to get some reasonable results in the preview. So you might want to change that. And then we can also toggle the exposure a bit here to make it a bit clearer what we're looking at. So the particle system has these three user inputs. It has the locations and the values. The locations are from the sensor locations, and the values are the live temperature values coming in from Azure. So, and then there is a neighbor grid 3D, which is like a bounding box that contains a grid that lets the GPU particles in the system know where their neighbors are. So that's also defined on the blueprint, like the extents of that. It's a blueprint in the world. So that one is here, and there's a world bounding box size here, and you can set the cell size for the grid. So that's how detailed you want the GPU simulation to be. And then in the system we have a particle emitter here. So the important things here are in the emitter properties, that this is a GPU sim, and that you have simulation stages turned on. The simulation stages is the stuff down here in green. So that's what lets the particles talk to each other and change their color and all that. And then in the system we have a particle attribute reader that lets particles read attributes from other particles, such as temperature and color. And then we have the emitter update. So the emitter updates once here. So it spawns the particles once, and then it keeps the same particles alive. It spawns the particles in a grid that has a grid size of world bounding box size XYZ divided by 20. So that means one cell every 20 Unreal units. And then there's a custom function here for coordinate transform between unit space and simulation space. So unit space is the coordinate space of the neighbor grid. So all of these custom functions, I grabbed them from the Niagara Advanced Content examples. So I don't think I changed anything. So we're not going to them in depth today, but they are available for you if you want to get them from there. And then it spawns the particles. It sets a scale, spawns them in a grid, and once the particles are spawned, the particle update triggers every tick that the particle system updates. And here we unchecked so it doesn't kill the particles when the lifetime has elapsed, so they stay alive for the duration of the system. And the only thing that's done on the update here is set the color. So we have a color curve applied to this, so that ranges from 0 to 1, and it maps the colors of these. So we can change these to maybe a beautiful sky color, which turns out to be not good at all for heat maps. So let's change it back. And then we have finally the simulation stages where the magic happens. So the first one here generates the neighbor grid. So that's also something I grabbed from the Niagara content examples with this custom code. So this one figures out which particles are neighboring other particles so that it's faster to query them, as far as I understand. And then this one, temperature influence. So if we uncheck the last one, we can see what this one does a bit more clearly. So this one sets the start temperature, like a seed temperature, where the sensor locations are. So that's also a bit of custom code. So if the length between the particle and the sensor location is less than 20, it sets the temperature. And then the last one, that's what sort of propagates the temperature out from these start locations. And then when they meet each other, they start to interpolate the color and all that. So there's a lot of complicated HLSL shader code here. So it does like a quadruple loop over all the neighbors during cells. It queries the particles. It just checks if the particle's already been queried and if it's greater than or less than distance from the start position and temperatures and all of that. So a lot of math. So this could probably also be done with a set of 10 custom nodes to make it a bit more readable. So I wouldn't recommend it doing like this. Another cool thing here is find nearest distance field. So this is what's causing it to respect the walls in the model. So it queries the distance field. It uses this one, distance field surface vector location, and it uses it down here. So it checks if it's close to a wall, it doesn't propagate the temperature in that direction. And then we have all the input parameters, and it outputs the temperature delta, which is used for the color. And then lastly, we have a mesh renderer, and if we uncheck this one, we get probably nothing. So the mesh renderer is fairly straightforward. It's a cube, and the cube has a material, and the material basically just sets the color and opacity. I don't think this node is being used. And then for this one, I also sort of want to show how this reacts dynamically. So now let's just first check that it works. Yeah, still receiving live data like before. And now if I just add a cube here to block off this doorway, just put like scale 2, 2.5 I guess, 0.5, and just drag this up so hopefully it blocks the doorway. And then we try again. So now the temperature doesn't find its way into that room because the door is blocked off. And then let's also see what happens if we just make this a bit wider and then we move it out to block off this part. You can see there's a sharp temperature divide there. It sort of propagates around that. And if you want to place and move around meshes at runtime, it would probably also react to that, which is pretty cool, as long as there's a distance field on the mesh. All right, I think that was everything for the temperature particle system. So now let's have a look at the HVAC. So actually, if we first have a look at the HVAC blueprints, they first have a mesh on them. And then if we hit Control B and go to the blueprint, we can see what this one looks like. So one of these are placed automatically by the editor utility widget at the start at the locations that were imported from the Revit model. And so these ones, they have a bunch of events on them. So when the live data comes up, there's an interface that's triggered here, and it sets the new values and all of that. And then the particle system itself is in a blueprint that has events that are triggered by the interfaces to update, and then they are being set, the flows and the temperature values are being set there. From there on, we can have a look in the particle system itself, and that on first glance looks similar to the temperature one, but it has a bunch more parameters coming in. So it has dimensions of the HVAC outlet. It has a spawn rate since there's particles flowing out, and it has some directions for which direction the flow is going. Other than that, there's the location, there's the temperatures, and there's the neighbor grid, so the particles can talk to each other. And then the emitter itself is also a GPU compute sim. It also has simulation stages on, has a particle attribute reader in the same way, but the emitters are a bit different. So this one has a spawn rate, so it continuously spawns particles. It has the same transform matrix function, and then the spawn, it initializes the particle and sets a color, and it sets a velocity here also. Sets a location, sets a velocity, and sets a start temperature. And then the update has a lot more stuff in it as well. So these particles have a lifetime, so they expire after a while. And there's some curl noise, which is just to give the particles a bit more waviness as they float through the air. There's some drag here that makes the particles slow down as they travel. And then there's avoid distance field surfaces, so they don't go towards walls that much. They avoid walls, and then if they do hit a wall, there's a distance field collision as well. So it's not that apparent in the model, but these particles, if there's a ceiling above, they would like float through and into adjacent rooms and that kind of stuff. And then there's a linear force, and this linear force is being calculated down here in the simulation stages based on a lot of stuff. And then there's a gravity force. So the gravity force is being set by the temperature, so that kind of hot air rises and cool air sinks. And then there's a velocity force solver that has some acceleration and speed limits. And then the sprite is scaled in the direction of travel by the velocity. And then the color is being set by a color curve in the same way. Let's see what happens if we change this one to a horizon color. So you can change this to whatever you want. Let's go ahead and change it back to heat map. And then the sprite size is scaled by the age, so they kind of particles expand as they get older. And then the simulation stages for this one, there's the same one, generate the neighbor grid, the custom function I showed. So that's identical, also from the Niagara Advanced Content examples. And then the flow interaction function, which is also sort of similar. It has the same iterating over the neighbor grid, getting all adjacent particles, but then the math is different. So this one more takes into consideration positions and velocities of the particle, and also propagates the temperature between adjacent particles and the surrounding air, so they kind of cool down depending on the room temperature. So again, this one is probably way too complicated, and you see there's some stuff that's not being used here. So part of this could be also done with nodes like this. I think you can't do 4 nodes like this, so the actual loop would have to be in here, but some of the stuff you can break out. And then finally there is a sprite renderer. So this one has a 2D sprite that's drawn on a plane. It just has, there's also, again, there's some stuff that's not being used in here. This is not being used, this is not being used, this is not being used, but particle color, and then opacity through a sphere mask, and then there is a texture that's being used for the refraction, so that it sort of has some subtle refraction effect, but again, not too complicated. So originally these two, you notice they are similar, so they were part of the HVAC and the temperature, they were part of the same system. So there were 2 emitters here, and they would both talk to each other, and the temperature would propagate between the particles and the temperature grid, and they would update back and forth in real time. But the performance wasn't great, and it also was very complicated to make any changes. So we sort of simplified it for the demo, but it works in theory, so you can have a full building particle and temperature field simulation going in a single Niagara system. Probably need a crazy GPU for that to run with any kind of performance though, but just to make you aware. And I think that was pretty much everything. I'll be available questions for there's anything you want to go more in depth to after this. But I hope that gave you some ideas for how you can use particle systems in Unreal to visualize real-time data. Of course, there's a ton of other ways to do it, and you can use other stuff than particle systems as well. But for the scope of this talk, I hope that gave you something to work with. So we are really excited about the possibilities of this. It's still sort of early stages, so we're looking at applying this to a real project and just replacing the mock devices sensor with some real sensor data. Shouldn't be too complicated. So yeah, hopefully we'll have something to show in the next year or so, but who knows? Anyways, that was all for me. Thanks guys for listening, and I'll see you in the questions.